Good morning, everyone. Allow me to introduce the Group 2 discussants and their topics. The discussants, I'm Patrick Arden Temporal, will be discuss the greatest common divisor. Joyce Legaspi will discuss least common multiple. Mark Anthony Mondia will discuss continued fraction. Mary Heidi Claire Hesole will discuss the Euclidean algorithm. Jennifer Rivera and Vince Carlo Tan will discuss the linear Diophantine equation. This chapter continues to deal with the divisibility theory. We begin by exploring the common factors of two or more positive integers. We establish the fundamental theorem of arithmetic, the cornerstone of number theory, and then turn to the common multiples of two or more positive integers. Finally, we investigate the important class of linear Diophantine equation. I will discuss the greatest common divisor. In this section, we define the greatest common divisor, or the GCD, of two integers and its properties. Definitions number 1. Two integers a and b, not both 0, can have only a finitely many divisors. Note that the divisors of a and that the absolute value of a are the same. The greatest common divisor of two integers a and b is the greatest integer that divides both a and b. The GCD of two integers a and b by quantity a and b, we also define as the quantity 0 and 0 is equals to 0. Example, note that the greatest common divisors of 24 and 18 is 6. So the GCD of 24 and 18 is 6. Here are some of the examples. The GCD 4 and 6 is 2. GCD of 42 and 0 is 42. GCD of 12 and negative 15 is positive 3. Two integers a and b are relatively prime if quantity a and b is equals to 0. The greatest common divisor of 9 and 16 is 1, thus they are relatively prime. Note that every integer has positive and negative divisor if a is a positive divisor of m and negative a is also a divisor of m. Therefore, by our definitions of the greatest common divisor, the quantity a and b is equals to the quantity of absolute value of a and the absolute value of b. Now, we are going to discuss a theorem about the greatest common divisor of two integers. This theorem states that if we divide two integers by their GCD, then the outcomes are relatively prime. For the theorem number 7, if the quantity a and b is equals to d, then the quantity a divides d and b divides d is equals to 1. It shows that a divides d and b divides d have no common positive divisors other than 1. Let k is a positive common divisor, such that K divides A over D and K divides B over D. There are two positive integers m and n such that A over D is equals to K times m and B over D is equals to K times n. We get that A is equals to K times m times D and B is equals to K times n times D. The next theorem shows that the GCD of two integers does not change when we add a multiple of one of the two integers to the other. For the theorem number 8, let A, B, and C be the integers. Then the quantity A and B is equals to the quantity A plus CB and B. We will show that every divisor of A and B is also a divisor of A plus CB and B and vice versa. Hence, they have exactly the same divisor. Let K be a common divisor of A and B. So, K divides the quantity A plus CB. L be the common divisor of A plus CB and B. So, L divides the quantity A plus CB minus CB is equals to A. Example, the GCD of the quantity 4 and 14 is 2. So what we do is we take the larger of the two numbers, which is 14. Then we set it to the equal to the smaller number, which is 4 times 3 plus 2. Then the next step is to take the number 4 to the other side of equals, and 4 is equals to 2 times 2. Then 2 is our GCD. Now, we present a theorem which proves that the GCD of two integers can be written as a linear combinations of two integers. The greatest common divisor of two integers A and B, not both 0, is the least positive integers such that m times A plus n times B is equals to D for some integers m and n. Assume without loss of generality that A and B are positive integers. So the set of all positive integers of linear combinations of A and B. So this is non-empty since A is equals to 1 times A plus 0 times B. And B is equals to 0 times A plus 1 times B are both in this set. Thus, D is equals to m times A plus n times B for some integers m and n. So by the divisions of algorithm, we have A is equals DQ plus R, where R is less than D but greater than or equal by 0. As a result, we conclude that if quantity A and B is equals to 1, then there exists integer m and n such that m times A plus n times B is equals to 1. Next is let a sub 1 and a sub 2 up to a sub n be integers not all 0. The greatest common divisor of this integer is the largest integer that divides all of the integers in the set. So the greatest common divisor of a sub 1, a sub 2 up to a sub n is denoted as the quantity a sub 1, a sub 2 up to a sub n. The integers a sub 1, a sub 2 up to a sub n are said to be mutually relatively prime if the quantity a sub 1, a sub 2 up to a sub n is equals to 1. Example, the integers 3, 6, and 7 are mutually relatively prime since the GCD of 3, 6, 7 is 1, though 3 and 6, or that the GCD of 3 and 6 is 3. The integers a sub 1 and a sub 2 up to a sub n are called pairwise prime for each I is not equals to j. We have the quantity a sub I and a sub j is equals to 1. Pairwise, pairwise prime, if every pair of the items in the list are relatively prime. Example, the integers 3, 14, 25 are pairwise prime, pairwise relatively prime, that is, the integers are mutually relatively prime. Before I end my lesson, allow me to read this quotation from Confucius. Tell me and I will forget, show me and I will remember, involve me and I will understand. Thank you and good morning po sa lahat.